How can one airplane show three different airspeeds at the same moment and leave its pilots without a reliable answer? One indication was falling while another was rising, and the difference eventually became enormous. The crew had to decide which information they could trust while still flying the aircraft. But there was something even more disturbing. If the airplane was still flying normally, how could its own instruments make the crew believe something else? The answer would eventually reveal that the problem was not simply one faulty instrument. It was a failure that could make multiple sources of information appear precise while no longer representing the aircraft accurately. And once the crew began responding to those numbers, the situation became far more dangerous. Shortly after takeoff from Moscow, Saratov Airlines Flight 703 climbed normally. At first, nothing about the flight suggested that the crew was facing an unusual problem. The aircraft was climbing, the engines were producing power, and the instruments appeared to be giving the crew the information they needed. But about 2.5 minutes after takeoff, at roughly 1,300 meters, the airspeed indications began to diverge. One indication began showing a different speed from another. At first, the difference was small enough to look like an instrument problem rather than an emergency. But the disagreement did not disappear. It grew. The crew now had two indications describing the same airplane differently. And that created a question that pilots normally should not have to answer in the middle of a climb. Which one was telling the truth? The difference eventually reached roughly 30 km/h. That alone was not necessarily enough to explain what was happening. But then the cockpit received another warning. The airspeed information was becoming inconsistent enough that the aircraft systems could no longer treat the measurements as trustworthy. The autopilot was disconnected. Now the crew had to continue flying manually. And that changed the nature of the problem. When an airplane is being flown manually, airspeed is not simply another number on a display. It is part of the information the pilots use to understand how the aircraft is behaving. Too little speed can create one set of dangers. Too much speed can create another. But if the instruments disagree, the pilots have to determine which indication reflects reality. And they had very little time to do it. The aircraft continued climbing. The disagreement continued. And then the numbers began moving farther apart. What had started as a small discrepancy was becoming something much harder to explain. One system suggested the aircraft was slowing. Another suggested something very different. The problem was no longer simply that one number looked unusual. The problem was that the cockpit was receiving conflicting descriptions of the same aircraft. And that raised a much more dangerous question. If two instruments disagree, which one is wrong? And how can the crew know before the aircraft itself begins telling them otherwise? The contradiction became extreme. One airspeed indication began falling rapidly. It continued downward until it approached zero. But another indication was still showing roughly 540 to 560 km/h. Now the cockpit was presenting two completely different pictures of the aircraft. One indication suggested almost no airspeed. The other suggested the airplane was moving extremely fast. The airplane could not simultaneously be at zero airspeed and traveling at more than 500 km/h through the air. Something was wrong, but the pilots did not have a simple warning saying, "This instrument is wrong." Both indications appeared as precise measurements, and neither came with a label explaining which one should be ignored. That was the real danger. If the low indication was accurate, the aircraft could be approaching an unsafe, low-speed condition. If the high indication was accurate, the situation was completely different. The crew had to interpret the aircraft's behavior, while the instruments they normally depended on were contradicting one another. And the difference was no longer theoretical. The lower indication continued falling. 34 seconds later, it reached zero. At almost the same time, the backup airspeed indication was showing roughly 540 to 560 km/h. One system effectively said, "The aircraft has no airspeed." Another said, "The aircraft is moving extremely fast." Neither could simply be accepted without question. The instruments were not necessarily independent witnesses giving different opinions about the same event. They could have been receiving bad information from a common source. That possibility changed everything. Because if the problem was inside one instrument, the other indications might provide a reliable reference. But if the same hidden problem was affecting multiple systems, the cockpit could be receiving several precise-looking measurements that were all misleading. And that was the question investigators would later have to answer. What could cause multiple airspeed sources to disagree at almost the same moment? And more importantly, why would the numbers behave so differently if they were all supposed to be measuring the same aircraft? The answer began to emerge when investigators compared the cockpit indications with the aircraft's recorded data and the conditions during the climb. The important clue was not one particular airspeed reading. It was the pattern. Multiple airspeed sources had become unreliable within the same general period. That suggested something more than an isolated instrument failure. Investigators examined the systems that supplied pressure information to the airspeed instruments. That led to the pitot probes. A pitot probe is designed to sense the pressure associated with the aircraft's motion through the air. That pressure information is then used by the aircraft's airspeed system to calculate and display speed. But the probes have a vulnerability. Ice. In freezing conditions, ice can interfere with the pressure information reaching the instruments. And on Flight 703, the investigation found that all three pitot probe heating systems had been left off. That mattered because the aircraft was operating in conditions where icing was possible. The discovery provided a common explanation for why several airspeed indications could become unreliable. The problem was not necessarily that three instruments had independently decided to fail at the same time. The problem could begin much earlier, at the point where the pressure information was being sensed. Ice could compromise that input before the cockpit ever saw the resulting number. Suddenly, the three conflicting airspeeds made more sense. They were not three genuine physical speeds. They were conflicting measurements produced from compromised information. But that only answered the first question. It explained why the numbers had become unreliable. It did not yet explain the most important part of the story. Why did unreliable airspeed information turn into a loss of control? The aircraft was still physically flying. The engines were still producing thrust. The wings were still generating lift. So the deeper mystery remained. How could incorrect information inside the cockpit lead the crew toward a situation from which the aircraft could not be recovered? The pitot icing explained the contradictory airspeed indications, but it did not physically push the aircraft into the dive. That distinction is critical. The aircraft itself had not suddenly acquired three different physical speeds. It had one actual motion through the surrounding air. What changed was the information available to the crew about that motion. Ice affected the pressure inputs. The pressure inputs affected the airspeed indications, and the indications influenced the crew's understanding of what the aircraft was doing. So the chain was not simply ice right arrow dive. It was ice right arrow compromised airspeed information, right arrow crew response, right arrow loss of control. That difference matters because an instrument problem does not automatically become an accident. Aircraft and pilots are designed to cope with abnormal situations. But coping with an abnormal situation depends on recognizing what is actually happening. And this is where Flight 703 became especially difficult. The cockpit did not simply lose every airspeed indication. Instead, it received conflicting information. One indication could move towards zero. Another could show a very high value. The numbers still looked like measurements. They still appeared precise. But the underlying information was no longer giving the crew a reliable picture of the aircraft's true condition. That created a dangerous decision problem. If the pilots reacted to the low indication, they could believe the aircraft was approaching an unsafe, low-speed condition. If they trusted the higher indication, they could interpret the situation very differently. The challenge was not simply controlling the airplane. It was determining which description of the airplane could still be trusted. And while the crew was trying to interpret the conflicting indications, the aircraft's attitude and flight path were changing. The margin for recovery was becoming smaller. The investigation, therefore, had to look beyond the frozen probes. The question was no longer, why did the instruments disagree? It was, how did the crew respond to those disagreements, and why did that response lead the aircraft into a steep descent? The most important part of the story was not that the aircraft had unreliable airspeed information. It was what the crew did while trying to interpret it. The pilots were not choosing between an obviously correct number and an obviously broken one. They were confronted with indications that looked authoritative. A number on a display can be dangerous precisely because it looks precise. If an instrument says 300, 400, or 500 km/h, the number feels objective. But a precise number is only useful if the measurement behind it is reliable. In Flight 703, the investigation concluded that the crew's actions in response to the unreliable airspeed indications contributed to the loss of control. The problem was therefore not simply the instruments failed. It was the instruments provided information that could still appear believable even though the underlying measurements had been compromised. That distinction is crucial. The most dangerous information in the cockpit did not look obviously false. It looked like data, and the crew still had to make decisions. As the aircraft entered the steep descent, the remaining margin for recovery became extremely small. The aircraft's physical motion was real, but the information being used to interpret that motion was increasingly unreliable. And that is what made the situation so difficult. The accident was not caused by 3 different physical airspeeds. It was caused by a chain of events in which compromised measurements produced conflicting indications. Those indications influenced the crew's response, and the aircraft eventually entered a condition from which recovery was not achieved. So, which of the 3 airspeeds was real? None of the 3 indications could reliably tell the crew the aircraft's true airspeed. The airplane itself had one physical state of motion. The cockpit, however, was receiving conflicting interpretations of that state. And that is what makes Flight 703 so disturbing. The danger was not simply that the instruments were wrong. The danger was that the numbers looked authoritative even when the underlying measurements had been compromised. Aviation depends on information. Pilots use that information to understand what the aircraft is doing and decide what to do next. But when precise-looking information stops representing the thing it claims to measure, the problem becomes much larger than a faulty instrument. The danger was not that the airplane had three answers. It was that none of them could reliably tell the crew which reality they were flying through.